feel free to make it due on Monday, but the contents of the homework will be useful for your exam. And not specifically as question wise, it will be a good practice for you to work on that. So you have to be responsible whether you want to do it or not. If you have a lot of things to worry about, then you can start on the weekend, but then you have less practice for the exam. But if you do it, it will help you. Okay, is that clear what I said? It's upside down. Well, I think you can, there is a, but why did it change? No one changed it, right? Hold on.
Is there a button?
These options in the video?
In the video?
Video options. The second.
This one?
Yeah. Settings. There should be.
It's just mirror flipping. Is there a button?
Like not left, right, there is one, right? You see the mirror my video.
Yeah, mirror is like flip. Like this. Left, right. Should I turn this off and start again?
No, I don't think that will change anything. Niranjan, do you see our video inverted?
Your image is inverted.
Okay. Advanced.
Oh.
Advanced in the top. No. Start again. Why would it do that too? Okay. And the meeting and so Niranjan will get out and come back, and hopefully our universe will be better.
Okay.
And meeting for all, no, right? Only so it's the camera. The other camera is working fine, right? So it's not Zoom.
Oh,
Yeah.
now it looks good.
Yeah, but this is the computer camera.
I see.
And the moment I put huddle cam. Yeah, is there an invert button in that?
In the remote.
Yeah, in the remote, is there an invert button? Oh, yeah, this is. Okay. Which one was it? Oh, yeah. So there is a invert button. I just push one after one. Yeah, which one? Is it at the bottom? That's all. Okay, at least we know it's possible to move. Okay, we have Nathan, so are you back normal, Nathan? Yeah. Did you say something? Kapila? He does the camera every day, so I'll wait for him. Okay, we introduced polymatrices last time, and we worked with different bases. And today I want to show a case where we will mostly work with without actually specifying the matrices, work only in the basis representation, and eventually try to get a motivation for the polymatrices. This is part of your homework. This is homework 5, whatever is due on Friday. So this should help. And this is also usually given as the motivation for how you get Heisenberg's uncertainty principle. Like how do you begin? How do you motivate it to begin with? So we will start with 2 by 2. And the idea is that if you take this limit of large degrees of freedom, this eventually gives you Heisenberg. I may not be able to do the complete limit, but usually in a quantum mechanics course, this fits in very well. So let's work with a. So this can be called. This was done by Schwinger first time. It's called Schwinger's periodic unitary operator or operators. And again, the idea is how can we motivate like a position and momentum operator physical IH bar somehow. So let's say there is an eigenset. So this is an eigenbasis, let's say. And in our way of doing it, here the notations will be the way we have been doing it. We will use the vector idea for the states, but immediately you can do this Dirac bracket notation. That's okay. Okay, so there is an eigenbasis. That is there are normal vectors, and there are tangent vectors, right? You can say this is covariant vector. That's a contravariant vector, and I can go all the way from 1 to 2 we don't specify how many dimensions there are. There are, let's say, n eigenvectors associated in this eigenbasis. And eventually you want to take a limit and tends to infinity, but that will be left as an exercise or a quiz. Okay. We are working in complex space, so we have the idea that EI dagger, that is the transpose and the complex conjugate, is equal EI. So if we start from the contravariant space, you get the covariant vector, and do the same thing in the opposite way, you get the other. So that's it, eigenbasis to begin with. But now let's say that is an unitary operator. So there is a unitary operator. And in general, if you have two basis vectors, you can construct unitary vectors operators in a way. But here we will do the simple idea that U acting on the eigenvectors gives you not necessarily the eigenvector itself. If it gives you back the eigenvector, then they are eigenvalues of this, or eigenvectors of this operator itself, the basis that is eigenset itself. But let us consider the situation where they shift itself. So if it is I equal to 1, this becomes I plus 1. If I is equal to 2, then this becomes 3, 3 becomes 4, and so on. So that's your definition of the operator. So if you were to check this out, so you have 1, let's say that's your E1, and that's your 2, that's your 3. It's just a label that is labeling the independent vectors, and U is basically going from here to here. So U acting on 1 gives you 2, U acting on 2 gives you 3, and so on. If 3 goes to 4, but then you have to specify what about n? Like at the end, you will reach n, so that I haven't specified yet what exactly happens to n. So I have to tell you that this is for I not equal to 10, n. If I was equal to n, then I get back U1. That's what makes it periodic. So if I was equal to n, then you do this. That's basically the definition. So again, n goes to 1, and otherwise it just splits. So this is the idea that it's a periodic unitary operator. That's the idea that after a while it brings it back. And that's your U. And now, so idea would be, let's find its eigenvectors. The moment you have an operator in quantum mechanics, you want to find the eigenvector, then you have an independent eigenvector, and the idea is that in that particular basis, it will be diagonal. Okay? So let's find the eigenvector. Once we have the eigenvectors, we can play the same game again. In that eigenvector, find another operator which does the same thing, and we will see how many operators can we construct like this. So let's see. There's one thing you can do. If you have U on E1, let's say En, like I start with n so that I get 1. Right? If I start with this, I get 1. If I do U square, I again apply this. Well, that's equal to U of E1. That's equal to E2. And I can keep doing this. And I learn immediately that if I were to do this for n times, n, I get back, right? So this will be equal to U raised to n, and I get back E n. So u multiplied on n gives me 1, but then I can also multiply it many times. Oh, no, this is wrong. What did I do wrong? Lot of this. This should be 2. Hold on. Yeah, this is correct. So 2 gives me 1, 2, and n gives me. No, I did it correct, right? Did this right? Okay. Yeah. Start from this, and this implies that this is an eigenvector of u of n, which means that un minus of 1 is equal to 0, or you can say n times, if I multiply u n times, I get 1. That immediately gives me something about the eigenvalues of u. So if a matrix satisfies, so let's think of A as a matrix, same idea as u, A square is equal to 1. Like this is A is a matrix. Square the matrix, you get a 1. Then what can you say about the eigenvalues of the matrix? Plus or minus 1, right? So this implies that so A prime is eigenvalue that's equal to plus or minus 1. What if it was A cube? Can you say something about eigenvalues? Yeah, so what Aryan is suggesting is that there are 3 solutions and they will be the roots of unity. The main idea is that eigenvalues satisfy the same equation as the matrix itself. For example, if you know that a matrix satisfies A square plus B times A, these are all matrices, but B, A and B are numbers. C times 1 is equal to 0. So A, B, C are numbers. Then A prime, which is the eigenvalue, also satisfies the same equation. Now this is algebraic. This was the matrix. This was an operator equation. Notice. Here it is an algebraic equation. We know how to solve for this. It's a quadratic equation. Okay. Tell me why this is true. That's a quiz problem. And here it will be again A prime cube is equal to plus 1. If A prime cube is equal to plus 1, as Aryan was trying to point out, the 3 solutions are, that seems to be 3 solutions, and they will be on a unit circle. Right? Think of a unit circle in a complex plane. So this is x, that's your y, z is equal to x plus iy, and divide this into 3 points. And that's your roots. So this will be equal to 1. A prime will be equal to 1. That's a solution. A prime is equal to, this is 120 degrees, which is basically 2 pi by 3. So this is e raised to I 2 pi by 3. That's this, that's 2 pi by 3. And if I multiply that by 2, if 2 times 120 degrees is 240 degrees. That's 2 pi by 3, that is 4 pi by 3. I can keep doing that. I can do the 3rd one, 4th one, 5th one, but then they will start repeating it. So there are 3 independent of them, and rest of them are just repetitive. So let's say quiz is why is this true? So A prime is quadratic equation, so it's minus b plus or minus b square minus 4ac divided by 2a. Why is that true? So try to motivate that or actually prove that. If you're able to prove that, that's actually true. Is it clear what the quiz is? Okay. Quiz is you want to find out why an operator equation immediately leads to eigenvalue equation. So that means I can get the eigenvalues of u of n. Now that I have an equation for u, I should be able to talk about u of n. So let's say u is u prime. I earlier said that eigenvalues always will be the prime of the operator itself. By making it small, so it's slightly unconventional, but I think it will be okay in this case. So we immediately know that u prime raised to n, whatever are the eigenvalues raised to n would be equal to 1. Now they are numbers nowadays. Now they are numbers. Raised to n is equal to 1. Here raised to 3 is equal to 1. You made the circle divided into 3 parts. If it is nth root of unity, you divide the circle into n parts. Okay. So for example, what would be the roots of a raised to 4 is equal to 1? That should be immediate. So if you have a matrix whose fourth power is 1, what are its eigenvalues? 4 points. 4 points on the circle, but what are they? Should be immediate, right? That's 1. I. This one is I. So you have 1, I, minus 1, minus I, right? Because that's I, that's minus 1, that's I. Check it out. 1 raised to 4 is 1. I raised to 4. I squared is minus 1. So I raised to 4 is also plus 1. Minus 1 raised to 4 is plus 1. Minus I minus 1 raised to 4 is plus 1, and I raised to 4 is plus 1. Again, that works out. Right? And same thing, you should be able to do this for this also. You should be able to show that this is raised to this is equal to 1. But in the exponential form, it is immediate, because whenever you multiply that, you get an exponential of I2 pi that comes out. So if you have u raised to n equal to 1, then you immediately know the eigenvalues. So what will the eigenvalues be? It is exponential of I, 2 pi raised divided by n. So divide the angle by n and then multiply it one after the other. So the first eigenvalue will be multiplied by 1, second eigenvalue will be multiplied by 2. So overall, I say multiply by k. For each k, I get, so I should put a 0 also, right? So this is 0, 1. Oh, let me try with 1. 1, 2, 3, and so on until n. So the nth one will be 1. The n eigenvalue will be e raised to I2 pi and be equal to 1. So that's e prime of k. So again, we have an eigen basis. I defined an operator like this. I called it a periodic operator. And you immediately find that eigenvalues are this, and then you ask what is the eigenvectors. And if you have the eigenvector, then you have a new basis. Right? Once I get an eigenvectors, I have a new basis for this. So let's do that. So use this space. Can I erase it? Here's this one. This one? Oh, okay. So we want to find the eigenvectors. So that's eigenvalues. So eigenvectors of u would satisfy u multiplied by, this time let's call that u of k, let's say. that should give me back u of k. That's a definition of an eigenvalue equation, multiply that by vector, gives me back the eigenvector, so this is, and it gives me the eigenvalue, so right? Notice this is a number, the prime quantities are numbers, others can be vectors or tensors, and the prime quantity is the eigen value. Let's do something immediately, since it's a unitary operator, so I can also do the following. Let me multiply by an inverse. Remember what a unitary operator is? Or let me not say anything. Let's just multiply by u inverse, right? So let's multiply this by the inverse operator on both sides, and immediately I get u of k is equal to divide the that we do this in two steps. It's u inverse dotted with u of k. That equation is also true, and what that means is that okay, writing it in a slightly different form, divide this out by 1 over u prime of k, that's a number, times the vector itself. What that means is that if so u and u inverse have the same eigenvectors, but they don't have the same eigenvalues. The eigenvalues are inverted in a sense. But in our case, it is simple because they are all exponential forms. The inverse of that is just a complex conjugate. So u and eigenvalues are and u1 over u prime of k is nothing but u prime of k star. And it's a complex conjugate because they are it's a periodic unitary operator. You can say. Multiply it again, and what we have is let me take a dagger this time. So this is take the dagger operator, the dagger operation. So then what I have is I have to multiply this out. So I say u of k dagger and multiply by u inverse, but these are unitary operators. So this will be just the dagger, so this will be u itself, and that is equal to this time take a star again. So this is star of this, and then get it back. So it is u prime of k and k. So this rewrite this, and we have u of k dotted with u. Just a simple manipulation here. Open. So I think I wrote this wrong. Oh no, I did write this. Okay. And this is u of k. So in this simple manipulation, what I've shown is that if an eigenvector, right, on the right side gives you an eigenvalue, if you operate that on the left side, you get the same eigenvalue, and it's just that now instead of a tangent vector, you get a normal vector, or if it was a normal vector, you get a tangent vector. So covariant vector becomes a contravariant vector. So using that, now we want to write our eigenvectors in terms of our old basis. So let's ask what exactly is the eigenvector itself. So we want to ask if u of k is your eigenvector, what is it in terms of your old eigenbasis? So I can immediately find that this will be equal to 1 dot with u of k itself. Like multiplying by 1 is a completeness relation. That is how you get the projections. So get the projections. So this is equal to summation L equal to 1 to n L. Yeah. And we will be interested in this, right? These are the projections. The projections of the eigenvectors u on the basis of the original eigenbasis, that is. If I know this, then I completely know my eigenvector. So let me find that out. So for finding that out, I have to use the operator u, right? Somehow I should bring in the operator u in here. So let's do that in second. Readable?
So when you applied this dagger operation, you said covariant becomes contravariant.
Yes, that was how we said this is equal to, like, it's like a row. I mean, if you have a column vector, becomes a row vector, and then you make a complex function.
So the superscript does not shift to subscript. It's okay.
Did I not change it? Did I? This one? Oh, no, this was an eigenvalue. The prime always means eigenvalue. So this is just a number. So I don't have to do this up and down. Is that clear? So if you want, yeah, I mean, there is no point in doing that. Like,
Okay.
if it's a number, then like what does up and down mean? So it's not necessary, or it should not be done, right? If you say 3, there is no up, 3 and not down. So yeah, I think that won't be necessary. Yeah. But again, nothing wrong in that either. We do it. That's okay. Okay, can I erase this part? So if I can I keep going here? Will it be readable? Let's see. Okay. Convention stop us in this thing. Okay, we would like to find this projections. So for that, I operate a new quantity. So let's say u of k is equal to summation L equal to 1 to n. I really don't need that summation because there is a L is repeated, but I'm going to manipulate this a little bit. So this is E of L and E of L divided with U of K. That's again a number, but E of L is the definition of U, right? If I use this, if I multiply U L times, I get E. So I can do the following. L equal to 1 to n. This is U divided with E raised to n. But now I have to keep operating. When I operate this once, I get 1. Second time, I get 2. Third time, I get this 3. So I have to do this L times. And then I have E of L. That should be perfectly fine. That's the definition of U. But now I have to somehow find my projection operator. So for that purpose, what I do is I know how to see the projection of U as on an eigenvector. So do it on an eigenvector. So make the projection U prime of K dotted with U of K, but that's not convenient because K and a K, it picks out only one, it sums it up. So let me change this, let me make it K bar. Just to use another variable. So like I want the projection of the first one, second one, third one, and so on. So this will give me whenever K bar is equal to K, that's the way to do that. That's equal to equal to 1 to n K bar out and dot product again. That's E of n. Now this is a number. And out. Okay. Advantage now here is that the else operator acting on U, I know how it operates. What is this equal to? This is an eigenvector. So what will this be equal to? It will give me back the same equation, correct? So U times U of K gives me back the eigenvalue of that. Right? Times that U of K. So basically I can get rid of all these operations. So every time I act on that, it gives me an eigenvalue. There are L of them, so I get L raised to the eigenvalue. So this is equal to L equal to 1 to n. This is U prime of K bar now raised to L. And this multiplies with this. Now these are projections. Notice these two are the same quantities. So I immediately know that I can find the projections. Like I'm interested in this projection. This is also the same projection in the reverse, right? So it is a complex conjugate of this quantity. So there seems to be n equations of my projections, but it is all on the right side. So this is a linear equation in all the projections. You can think of, if you can see through those equations, there are n equations and they are the projections. So now I need to invert them. So before I invert, let me do some manipulation of this. Notice these are my eigenvalues raised to L. So that's exponential factor. So let me do those things. So this is, what is this, by the way? These are the eigenvectors of my U. When they are dotted with each other, what do they give? If I have 5, delta function, right? They are orthogonal. Eigenvectors by construct, or they can always be constructed as orthogonal vectors. So this is the orthogonality of those eigenvectors. So this is nothing but delta of K bar K. And this quantity does not depend on the sum L. I can bring it out. I'm going to bring this out and write it in the denominator. It's a number, K bar, dotted with E of n. And that's equal to the summation of L equal to 1 to n. This is exponential I 2 pi over n, K bar of them, and raised to L, that's this multiplication on an exponential. And that's the number. Again, these are linear equations. This is what I'm interested in. These are the projections. These are linear equations. These are numbers. And this is on the right side. So x plus y is equal to something. X minus y is equal to something. I can solve for those. But I can do this in a better way. And that is if I make the observation that these are nothing but Fourier transforms. this is a Fourier transform of this quantity, and that's the Fourier transform. These are discrete Fourier transforms. Usually you might be, at least if you've done quantum mechanics, we tend to do the more sophisticated Fourier transformation where these are integrals. Or this is one of them is an integral, one of them is discrete. This is discrete Fourier transformation. Even if we don't know Fourier transformation, we don't realize this is a Fourier transformation. Let's do this as we would in a Fourier transformation. Let's just do algebra. So I'm going to multiply this by another exponential. So let's say with respect to L bar, right? So I multiply exponential I 2 pi over n and k bar. So the summation was in L. I don't want to use that, so I use L bar instead. So I'm multiplying this on both sides. This is the trick of Fourier transformation, which we will see this in a slightly more from the scratch in a sense later on, but here we are just using it.
What the eigenvalues this one
In this row, what
in this form? E to the I to the
because we did this, right? Because they are eigenvalues of u, because u of u raised to n is equal to 1. So its eigenvalues has to be the roots of unity, so they are exponential. So we have the eigenvalues to be this, and now we're finding the eigenvectors. Eigenvectors requires the projections, and projections we say is a Fourier transform, but let's not pretend we know Fourier transform. So we just do the simple algebra that's needed to invert a Fourier transform, right? So we are pretending as if we don't understand what Fourier transform is, so we're not writing the answer immediately. But what you would do is you will multiply this out by think of you doing a problem, right? So x plus y is equal to 1 and x minus y is equal to 2. So you manipulate them, right? You first multiply, so let's say this is 2. First you will multiply this by some number, and then when you subtract it, it cancels out, right? So there is a choice that you make. So that's what I'm doing at a very generic level. If I were to multiply this, there is something that happens in there. And we want to use an orthogonality there, so I'll tell that in a minute. So currently I'm just multiplying on both sides, and I'm going to leave some space here. So this is L equal to 1 to n. And since there is no L inside this, I can bring it in. So I do I, and since I will need cancel, let me make it minus. There was a plus, I made this a minus. This is the standard thing you do in whenever you get something like a Fourier transform. This is L bar now and exponential. Oh. Once I multiply them, you notice that it is L bar minus L. So let me I can do this in a single step. Hopefully it's not confusing. L was L, I multiply this, so it is an L minus L bar, and exponential L. That's a true statement. Since this is true, I just multiplied it by an exponential here. But this at this point, I say I now want to do a sum over k bar. Once I have this, I do a sum over k bar. Like this is the idea that you first multiply by the 2, and then you want to add all this vertically, right? When you add them all, they all go to 0, and they give you any answer in your x. So that's step. You're doing it in a very generic way, and whatever I do on the left side, I do it on the right side. And by doing that, what is happening is that k bar sum is only in this exponential. There is no k bar here. So let me rewrite that if I can. Is this readable, Niranjan?
not that clear, but I'm following.
Maybe just zoom it in maybe, I think it's maximum.
Oh, that helps.
Okay, so then I can write one more step here, right? Okay, so this is equal, so this is L equal to 1 to N L to K, and basically I am earlier I was doing L sum first and then the K bar sum second. This time I'm doing K bar sum first. And why I'm doing this slowly is so that I can give you a sense of Fourier transform, which we will see somewhere else again. So I observed that this sum K bar is only acting on this exponential. This one doesn't have any K bar. I first do the K bar, move all the K bar dependence onto the right. This is my sum, and then I will do that if I can. These are exponentials. Adding exponentials are typically possible. And the question is, what is the sum of this exponentials? If I add a bunch of exponentials, what will I get? Exponentials are cosine and sines. If I do the sums, so this should be given as a quiz. These are sine and cosines, so they will always add up to 0. Okay, so this is a quiz for you. So you show that this can be seen as, like, remember again, that if you have 3 roots, these are the 3 roots of unity. If I add them all 3 as vectors, what do I get? 0, right? These 3 vectors are equally distributed on a circle, they will add up to 0. All the roots of unity always will be equally distributed, they will satisfy the vector equation that they could all add up to 0. Okay. So these quantities, whenever you do this addition, will be equal to 0. Except there is a condition there, right? It's not always 0. If L was equal to L bar, the argument of the exponential is 0. And then it is 1, right? Exponential of 0 is 1. If I'm adding those quantities, I'm not getting a 0, I get 1. So what it seems is happening is that exponential of I 2 pi over n times, let's say, m and, or what could I write, say, L and K, the L and L bar. There is a K bar also there, it doesn't matter, so I can write that K bar also there. If I were to sum over K bar, actually K bar should be there, so this K bar is equal to 1 to n, this is equal to, if L was equal to L bar, that's just n. And if L is not equal to L bar, that's equal to 0. If that's the case, then that's nothing but, you say this is n times delta of L bar. Or let's say L bar. That's what you would do. If I use that in here, this is equal, n comes out. This is a delta L bar, but I can use that to sum this. So this is E of L bar started with U of K. So because this was true, I could actually evaluate this median. And those were my projections. I was interested in those projections, so I have an equation for the projections now. And let me go back. Step. In all this just to evaluate the eigenvectors. You had this U, which was being written in the eigenbasis of E, and then we needed the projections, and we now have the projections. So U of or E of n possibly. So L bar probably dot with U of K is equal to 1 over n. And there is a summation here also, there is a delta function, so it is the exponential e raised to minus n pi k L bar over k. What did I do? Yeah, I did the sequence. Like k bar becomes k. Replace L with also with L bar, so I can change all the L bar to L, so that's fine. So that's my projections. Let L be equal to n. Yes, if I write L is equal to n, what I learn is that E of n dotted with U of k, and the complex conjugate of that is U of k dotted with E of n, is the complex conjugate of each other. That's equal to 1 over n, and that's nothing but 1 because L is equal to n. So I have my projections. If the square of this is the complex conjugate, remember, if I dagger this, I get this. So U of k, or let's say U of n, k, no, substituted this there, so k is equal to 1 over n. This is 1 over the square root of n. Is this correct? What is missing in here? Notice this is the star of this. If I have this as x, this is x star. That's a z complex number. So z and z star. If z times z star is equal to a, then z is equal to a square root of a. Is that correct?
Absolute value.
Absolute value, right? That's correct. Very good. So that should be an absolute value, which means that absolute value always is z is square root of a times exponential of some I alpha. Right? That's what it means. There's a phase there. So this is not completely true up to a phase. So we'll sacrifice that phase. If that's true, put it back in there. So I have my projections. K is equal. I will substitute it in there, 1 over square root of n, that makes it 1 over square root of 11. Exponential minus I. So I have figured this out, which means that my eigenvectors, these are my eigenvectors. First we found eigenvalues without really getting an actual matrix representation, right? We are just doing it in, at an abstract level. So okay, let's equal summation L equal to 1 to n. This is the projection, and this is the 1 over square root of n exponential and minus I n a times L, and these are minus, right? What is that? Minus is minus. Yeah, this is minus. Check in your homework. Hopefully, I did type this for you. So L and L. So whenever you have a eigenvector, I can write it in terms of my eigenbasis E, and that's your expression. And that's a Fourier transform. If you want to make that observation, this is a Fourier transformation of one and the other, and that happens only if this is a periodic operator. So as a summary, if I were to do, so this is all this to get the eigenvectors, but now we want to do something more, right? So this was not the complete exercise. So if I go back and tell or summarize what we have done at this point, we have a unitary operator which was defined in this way, and we now have u prime of k is equal to exponential of I 2 pi over n times k, and eigenvectors are u of k is equal to 1 over square root of n, L equal to 1, and exponential minus I 5 and L k. And E. So that's a summary, like we went ahead and did a lot of manipulations to get these eigenvectors, but now once I have my eigenvectors, that's a new basis. I started from a basis, I got a new basis. If I have a new basis, I can play this game again. Like I can do this again. So this time I have another circle. This time let me call. So this was E1, this was E1, E2, and so on. But this time I say this is U1, that's U2, and U3. And do the same idea, that this time there is an operator V that does this. And the only difference I would say is that instead of upstairs, let me make this downstairs so that I can pull this all together. And again, do the circle, that's your N. And our definition now is that V, operator V, acting on, like that on the left hand side, right? U, no, U, right? U, I dot with V be equal to U of I plus 1. Or it will be equal to U of 1 if I was equal to 1. Same idea. And you can show, so I won't repeat this whole exercise because then it is exactly the same, except that instead of E, I have to put a U. And instead of a U, now the eigenvectors will be V. So again, eigenvalues and eigenvectors will be V prime. So it is V of K. Again, there is a V raised to N will be equal to 1. So all the arguments go through again. I get this to be I 2 pi over N times K. And the only difference that comes is that here, instead of this being upstairs, it is now downstairs, but then I can lift it back up by complex conjugating. So let me write this first. So this is V of K equal 1 over square root of N. Of K. Complex conjugate this, or you go from, you make a dagger operator. That means that V K is equal to 1 over square root of N. Okay. If all this has to be true, you can, there is a small step in between that you have to actually show that E is equal to V. That you can show. I'll skip that. So maybe quiz. Show that E of L that we started with are nothing but eigenvectors of V itself. Because for consistency, if I were to Fourier transform this, I should get back this. So it will come out to be this. So now we have two operators which combine together to give you this. So now let's do some construction with, so now we have all the basic ingredients needed. And now let's try to do some analysis here. So we have constructed two operators, U and V. Have position and momentum operator, like there's a position basis, momentum basis. Think of that in your head, but these are not really position and momentum in the sense that position, or maybe I should ask this separately, right? No, not that. So let me not do that. So this is U and V. These are finite dimensional matrices. Position and momentum are always infinite dimensional matrices. So let's have U, and now let's say there is a function of the operators U and operators V. Whenever I have a function of an operator, I can expand this out, Taylor series. That is an A naught. I can have a linear piece in here, so that's A1 times matrix U. Then I can have V, let's call that B1 times another operator V. And next I can have combination, right? I can have combinations of this. So let's say C1 times U dotted with V. Or I can have D1 times V dotted with V. That's all the combinations I can have in my U and V. What I mean by that is when you're squaring it, there is also a possibility that this should be 2, right? So that's 2, D2, and let's say A2 times U squared is possible. And then there is B2 times V squared is possible. But U squared is 1. So that goes back to A naught. Any higher term in this is not there, it is going back to this. So when I do a Taylor expansion, I only have these 4 terms. And this quantity, so I cannot build anything else. So at an operator structure, I can have only an identity, I can have a U and a V, and U dotted with V and V dotted with U. And we will show that V dotted with U is not really the same, it comes out to be the same as U dotted with V. And due to that reason, there are 3 operators plus an identity operator. That's all you have. Let's do this. Maybe, yeah, so at least in the last 5 minutes, let me motivate. How do you get the permutation relation? So let's take U times V and multiply it with, let's say, U of n, U of k. That's something I can do. This one? This is, oh, that's V, the same V, my bad. And let us also do V dot with E dot with E. The second one is easier because this is an eigen vector for U. So I will have U prime of K times V multiplying with E of K. On the first one, I can do this because V multiplied by U, it only increases by 1, right? So this is equal to V multiplied by U, this is equal to U prime of K times U of K plus 1. That's a periodic. Do the same thing on this side. You now do first, you do the prime. Why am I missing something here? Let's see. Okay, U started with V will give you U of K plus 1. Yeah, no. So this is now eigen vector of K plus 1, and you will get U prime of K plus 1 times U of K plus 1. These two seems to be the same, except that this is exponential of I 2 pi raised to n times K plus 1. And this one is simply K times if I were to subtract these two quantities, V of V started with U, what I'm seeing is that there is an exponential of I 2 pi over n. And there is a U of K that's there, pull it back out, and what you get here is more. And now, or let me not put it like this. No. Let me subtracting this out, right? So subtract this out, multiply this out. So what I'm getting the exponential. And in the last 2 minutes, let me quickly know that if n was equal to an exponential of I25 over n, it's simply minus 1. So that means that u v is exactly equal to minus of v dot z, which is not normal for numbers, right? Anti-commutation. And remarkably, like this, I won't do it here. Another quantum mechanics book, what you can show is that in the n tends to infinity, if you take this up as a challenge, I think it's a good exercise, it takes some effort. You can show that you the v actually is exactly equal to v dot under. So you start with an anti-commutation, but as you go in the limit n tends to infinity, you get back to your classical mechanics, right? So if your position and momentum were not satisfying the anti-commutation, then you get. And in between, the eigenvectors will give you the anti-commutation also. So that's kind of a nice process you can. So that's sort of at a very abstract level of quantum mechanics operators showing up. And this is also there in your homework, so you should be able to put some more effort into this and try to see. This is also available in, there is a book by Schwinger's lecture notes on quantum mechanics, and that the first chapter has this construction in there. Maybe not exactly in this form, not in this notation, but it has a structure in there. I'll stop the quantum mechanics part with this lecture, and next time we will start with either complex analysis or Green's function. There's a good chance I'll start with Green's function and then do the complex analysis. I had to decide. I have one more week to. So next Monday we will start complex numbers, or if I do complex numbers, maybe do very quickly so that I can have time. Thank you.
Thank you, Dr. Sajesh.
Thanks, Niranjan.
See you next time.
Bye.
Dr. Sajesh, next, this Friday, you guys have exam, right?
Yes, yeah. So we won't have a class, correct?
Okay,
Yeah.
thank you.
Yeah, yeah, we won't have a class on Friday. Yes, yeah.
Thanks.
Okay, so see you on Monday or Thursday, maybe, right? Yeah, Thursday
Yep.
or Monday. Okay.
Bye.
Bye.